Welcome back to our lecture series on advanced hydraulics. So, we are going through the fifth module, that is channel transitions, or in fact according to the syllabus it was given as flow through non-prismatic channels. So, in this particular portion, in the last class we had discussed the effect of flow in open channels due to channel transitions, especially like the sudden transitions that we had elaborately discussed it in the last class. The sudden transition, how this due to the sudden transition in the channel, the effect means flow is getting affected. So, the sudden transitions that were dealt were sudden rise in bed elevation, sudden dip in bed elevation, sudden constriction in width, sudden expansion in width. So, these four cases we had elaborately studied them in the last class. We have mainly used the energy equations to analyze these things. Okay. So, today we are going into the next part of the channel transitions, that is mainly we will be continuing the channel transition itself, but instead of the sudden transitions we will be talking about the channel transitions like culverts and obstructions that arises in any particular flow stream. So, you know, means by this time you may be aware what is meant by a culvert or what is meant by an obstruction and all. So, the effects of the variations in open channel flow due to these structural elements, due to their interactions with the water body, means how it is getting affected, that we will be briefly going through. We are not going through the sediment transport process or the sediment deposition or erosion along these structures. We are only going through the open channel, that is flow processes occurring there. So, first we will be dealing with flow through culverts. So, culvert, it is a type of channel construction that are used in many engineering projects. If I just try to draw it for your benefit. So, if there is any natural drainage, small drainage or channel that is draining water from upstream to the downstream, if you have that, and if there is any particular engineering project in which that particular project demands passing through this particular drainage. So, it is not advisable to block this particular natural drainage that is available there. So, therefore, you will provide, if this is a small drainage, you will provide some type of culverts that can allow the drainage, and above the culvert the particular project will be implemented. Such type of projects, means engineering structures are built across the natural drainages or even the man-made drainages, so as to avoid blocking of the drainages and all. So, what they say here, if I want to, means if we can construct a if the drainage is like this, and if we construct a culvert of this form, then you can easily allow a road to be built across through this drainage and all, right. So, you can, so water will flow through this culvert without, and this road is not going to block the drainage, natural drainage of the path of the water also. So, that is, the culvert will allow drainage of water from or towards a water body or its natural path from upstream to downstream and all in the site of that engineering project. If the culvert would not, if you would not provide culvert, what the engineering project will do is that it will absolutely block the natural drainage path. Say, this is the natural drainage path of water here. In this case, this is the natural drainage path. So, if this block through an embankment, if you build a road along this direction, so this would have completely blocked this. Means, even though the channel width or the natural drain width may not be that much, it is still contributing to some water body or some other, means it is still draining to some water body or to a river or to a main channel and all. So, if that way it is advisable you do not block such natural drainage drain paths and all. Therefore, you can get enough quantity of water in your water resources or reservoirs and all. So, therefore, that as mentioned here, you can have say a road is being built like this with sufficient this thing. So, this is the road. You can have, say, you can talk in terms of highway also. Now times it is the time of highways and expressways and all. So, you require very wide roads and all, and still there may be many natural drainages that may get blocked due to this particular roadways. Therefore, if we provide a box culvert, for one example is a box culvert, it is in the shape of, means the natural drain of water is in this direction, it is in this particular direction, water is flowing like this. So, we provide a box culvert that will, it is a engineering structure, means you can have the box culvert like this, water will flow through this and it will cross and it will reach at this location. So, water can reach at this location. So, like that you can provide box culverts or any type of culverts. What is the peculiarity of culvert? Culvert, if you look at that, culverts, they are a unique type of constriction. So, what is meant by constriction? The word constriction, means what do you understand from this particular word? That is the path of the flow or the flow of water in a channel or in a river, they are getting constricted, that is through a width, means the width of the channel it is getting constricted, that are called constriction. So, you might have seen, say if I draw a particular this thing from the above, if there was a natural river like this. Now, due to some requirement, man-made requirement, either it can be man-made, some of the natural constrictions are also there in some in wide rivers. We are not talking about that. The man-made things, suppose some engineering construction is being built, it is required so that that particular channel remains stable and all for certain purposes. So, here the natural the drainage path, means water was flowing in this much width, say B here, B1 here, and all of a sudden it is getting constricted to another width B2, then it is coming out from that constriction. So, such constrictions are provided in many engineering projects. So, culverts are also a type of constrictions. If we just try to elaborate the constriction forms and all, you may see that say a sort of embankment is being provided with certain dimensions and all. So, the natural flow path was quite wide, but however, due to the in this particular river, say in this river, you were having water coming from this much width like this, it is coming here and it is getting constricted, means it is flowing now in a constricted path, then it will come out like this. So, this particular structure, this is a constriction. So, it is constricting the flow. So, we have already seen in the last class flow through a constricted way, means sudden constriction in the width of the channel and all. So, those things we have studied. So, culverts are also a particular type of constriction, where the entire system it is being closed, means that is the culvert is a closed constriction. We can say culvert is a closed constriction. Fine. So, culvert, it will act as open channel. That is, it will act as open channel if the flow inside the barrel is partially full. So, I hope now you can understand. Say, as we mentioned in the box culvert earlier. So, the culvert, it is a box shape. So, it is being provided like this. Water, it is getting drained through the culvert like this. Water will flow like this and it will come out, right. So, this is the barrel of the culvert. I can now say that. So, this portion is the barrel of the culvert. So, if the barrel of the culvert, if it is full, if the water, entire water, if it is full like this from here inside this thing, then the culvert will not act as an open channel, means you cannot call the flow inside the culvert as an open channel flow, you have some constrictions there. So, if it is partially full, if the flow depth and all, it is only partially, it is filling this partly only up to this height and all, and the flow is being maintained in the culvert, which is the case in many of the culverts. If you design many of the culverts, that is the better situation we require. Such flows are open channel flows, and you can use the open channel mechanisms to understand the culvert this thing. So, how do you suggest the thing, that is, what are the flow in culverts? How do you know whether the flow is full or not? Or flow in culverts is controlled say by the inlet geometry, so again I am just drawing the thing here. So, you have the inlet water coming like this, this is the outlet of the culvert. So, the inlet geometry also plays an important role. Inlet geometry, then the slope of the culvert bed, slope of the culvert bed. So, if I take a section along this particular plane, if I say take a section along like this, along the middle a plane, if you take this can be elaborated now, I can draw it. So, it will look like this. So, you have the depth of the barrel, which may be called D, you have the length of the culvert, which may be called L, then the slope of this culvert, you can call it bed slope of the culvert as 0. So, the slope of the culvert bed, that is also important. Size of culvert. So, what is the size of this opening given to here? The opening given here around these portions and all, what is the size? That is also quite important. Then you have another important this thing, the approach condition there. This is the inlet condition or the approach condition, and the tailwater, outlet or tailwater conditions. So, those things are also important, approach and tailwater conditions. They also play significant role in determining the type, determining how the flow is occurring in the culvert. So, usually means compared to the mathematical analysis and all, it is significant, it is important to have sufficient laboratory and experimental analysis on flow in culverts. Actually, the mathematical analysis are not much developed at this particular stage. If you are capable, or if you are, it is not about the capability. If you are motivated, you can just give a new try to incorporate more realistic mathematical approach to the flows in open culverts and all. Right now, many of the documented literatures have works mentioned especially on laboratory and experimental analysis. From that, they have inferred what could be the type of flows and all. So, that is, if you go through the history and types of various studies. So, various studies on especially experiment studies, culverts, they suggest some of them are, some people have used pipe and box culverts in their studies. So, they have used a fully pipe, you might have seen cylindrical pipe in some of the road embankments and all, or the rectangular box type and all, fully include this thing. So, pipe and box culverts are used. Some use round, smooth pipe culverts. So, there are many literature works related to such culverts and all. There some have used corrugated pipes or concrete and concrete materials and all, concrete pipe culverts. There are even reports of steel culverts and all used in some of the locations. So, that based on your interest, you can further go for the higher journal papers and all, and try to investigate the flows in culverts and all. So, we can now suggest culvert, the flow in culvert, that is, you have seen that this is the inside the culvert barrel. So, this is the depth of flow. So, inside the culvert, so water is coming like this. So, this is the vertical section of the culvert provided here. So, the depth of flow in this portion inside the barrel, it can be either partly full or it can be full, right. So, we can now suggest culvert will flow in full conditions. For the following two cases, that is, you have the inlet portion here, you have the outlet portion here. So, when the outlet is submerged, you have, that is, if the outlet portion, if it is submerged, if the water depth and all here it is this much submerged. So, you have a submerged condition, then the culvert may flow full, or when the head water or the inlet water condition, if the head water is high and the barrel is long, you may have full water condition. So, if the water in the inlet, if it is much higher, then you will see that it may flow fully. So, these conditions may suggest that the culverts may flow in a full situation. Next, we can suggest that the following conditions are, say, especially if you refer Venti-Chow's book on 1958, Venti-Chow's book on advanced hydraulics and open channel hydraulics. So, you can see that especially from various laboratory investigations, he has suggested that the entrance of an ordinary culvert will not be submerged if the head water is less than a critical value. What we want to suggest is that again the vertical section, the head water, say even if the head water is little bit above this location, the culvert barrel means barrel height, this location and all. So, this is the barrel depth. This raising, if the head water, if it is above the water level at the or the top portion of the culvert, does not guarantee that the flow inside the barrel will be full. It does not guarantee that. It requires another mandatory condition, that only the condition that if this height of water is above a certain critical value, then only the conditions will help to make the flow in culvert as fully filled conditions and all. So, we can suggest that condition H greater than H star only will help full flow conditions. So, we can now also suggest that this H star, from many of the experimental investigations, they suggested that this H star varies 1.2 to 1.5 times. See, again I am redrawing this. This is the culvert depth, this is the headwater depth. So, headwater depth should be above H star, that is the criteria, right. So, H star from various experimental investigation they found that it is approximately around 1.2 to 1.5 times of depth of the culvert. So, culvert some of the experiments also suggested that culvert with square edges rather than round edges and all, if it has square edges at the top of the entrance, at the top of the entrance, at the top of the entrance, if the edges of the culvert are square like this, many experimental investigations suggested flow will not be full in such culverts. So, mostly the flow will be below headwater level. So, what happens is that even though if the headwater, if it is above a certain value in such square conditions and all, it may dip inside this thing, it will dip, it may give an orifice type of flow inside the barrel of the culvert, and then it will exit from the outlet portion of the culvert. So, such situations can form, or it may act like a sluice gate. In the sluice gate, as you know that if the shutter is being raised or lowered, when it is lowered, you know that water will gush out, isn't it? A similar phenomenon may occur for such square edge types. Here the water may come like this, it may gush out like this and go on. So, this may be initially it may be very high speed, then due to the length, as it progresses along the length of the barrel, its energy decreases and its subsequent velocity decreases, you will get a reduced flow and all. So, we can suggest that the high velocity jet will continue through the barrel length. So, this is the length of the barrel. So, even if it is H star, H at this square edge entrance, top of the entrance and at the top portion of the entrance, even if it is square edge, we can suggest this as capital D or small d, whichever be. So, the high velocity jet, you can just give it in a different color. Here this water portion, it will go like this high velocity jet. So, that high velocity jet it will continue through the barrel length. It will continue through the barrel length. It will continue through the barrel length like this, and it will come out. However, its speed reduces due to loss in head, due to loss in hydraulic head, right. So, those conditions will suggest the thing. Now, based on the culvert length, based on the culvert length and the flow types in the type of flow inside the culvert and all, you can classify the flow in culvert. Means usually, again I am just redrawing the same thing. So, this is the length of the culvert and this is the depth of the culvert. this is the H, capital H is the headwater depth, and you can say this here, let it be the tailwater depth YT. Okay. And let this the slope of the bed of the culvert be S0. So, if this is the flow occurs from this direction to this direction. So, in this case what happens is that we, based on this thing, if we can suggest, if the culvert length L, if it is sufficiently not long enough to allow the barrel to be full. If this length of the culvert, if it is not sufficiently long enough, so that the flow inside the barrel becomes full, if it is not allowing that, then such culverts are called hydraulically, can write it like this, hydraulically short culverts. So, basically you can suggest two types of culverts, hydraulically short culverts and hydraulically long culverts. So, that is vice versa is, if it allows full flow, then such culverts are called hydraulically long culverts. So, this is the two main classification. Flow in a culvert can be hydraulically short, or you can suggest that the culvert, the type of flow in the culvert, it can be hydraulically short or it can be hydraulically long. From these two classification, we can suggest what are the criteria for hydraulically short. That is how the flow in culvert becomes hydraulically short, or how the flow in culvert becomes hydraulically long. So, hydraulically short or hydraulically long culverts are determined as follows: based on the length of the barrel, based on the culvert bed slope, based on the culvert size, based on the entrance geometry. You have seen that how you can have circular shape, you can have rectangular shape, square shape, various shapes or various things. So, headwater conditions, also the entrance, in the entrance what all other features are there, entrance and outlet conditions, they also play a significant role whether the flow in a culvert is hydraulically short or whether hydraulically long. So, these are the following some of the conditions. So, you can please note them. So, based on this thing we can classify, we can now classify flow in culverts as, say one is type 1. So, the type 1 flow means where, please recall the culvert diagrams and all. So, we will just give a detailed explanation now further. in the next slides and all. So, just recall this. So, where the outlet is submerged, such types of culverts flow are called type 1 flow. You can have type 2 flow, you can just give any either Roman letter or you can give Indian numerals and or Arabic numerals. You can have type 3 flows. In both type 2 and type 3, the outlets are not submerged, but they are different. We will see that. Then you can have type 4 flows. Type 4, these type 4 flows are encountered where the tailwater depth is, higher than critical depth. You can have type 5 flows, also type 6. I can just mention both together here. So, there are basically 6 types of flows in culverts. So, type 5 and type 6 are where the tailwater depth is lower than critical depth. So, the tailwater depth is lower than critical depth. So, these conditions I can now suggest it again. So, we can, so the type 1, this here I can just say type 1 flow, how it is encountered. Give the following this thing now. So, let this be the water depth here and let this be the water depth here. So, you can now suggest based on this bed of the culvert, this particular depth is tailwater depth, this particular depth is the headwater depth, and this is the culvert depth equal to D and culvert length L. Flow is basically occurring in this direction from upstream to downstream. So, here this is called type 1. This is, you can see H, that is the headwater depth, it is greater than D, that is the depth of the culvert. Similarly, the tailwater depth, this is also greater than D. If both the conditions are both the headwater and tailwater depths are greater than the depth of the culvert or the depth of the culvert, then definitely inside the culvert the flow should be full. Mainly it acts as a flow is full in such conditions. So, this is type 1, it is more like a pipe flow. Here you cannot apply the open channel principles to find the type of flow inside the culvert, because it is a constriction, means all around it is bounded. So, it is more like a pipe flow, you have to use the pipe flow principles. In the second condition, same thing. So, type 2, if I give it as type 2. So, what is type 2 flow? In type 2 flow, what happens is that your headwater depth, it is so this is your headwater depth, the depth of the culvert is given, flow is occurring in this direction, and inside the culvert it is almost full. Here the tailwater depth we suggest that the water flow is occurring like this, and from here the tailwater depth is this much. So, let us assume that this is the tailwater depth and the flow profile is in this form. So, what happens here is that we are suggesting that H should be greater than H star for full flow in parallel, right. So, we are suggesting H is greater than H star. Your y t, it is less than the depth of the barrel. So, these two conditions will make the flow inside the barrel full flow itself. Here the culvert is hydraulically long. Outlet is also, you can note the points. Outlet is unsubmerged. It is not, say the outlet is not submerged here, right. So, these are called, this such type of flow is called type 2. So, you have headwater greater than the critical value, you have this headwater greater than the critical value, you have seen that H star is the critical value, then only. So, for that will ensure full flow, it is not ensured, that is a criteria. Then you have the tailwater that is less than the depth of the channel, then you have the bed, means flow is full here, culvert is hydraulically long. The next type which we can discuss is type 3. So, let me give this as type 3 here. This is called type 3. Type 3 flows in culverts. So, what is the peculiarity of type 3 flows? Here, although you have depth of headwater depth h like this, here h is greater than the critical value, still what happens is that the flow inside becomes like this. So, it will gush like this, then it will flow like this, then in the outlet it will come and drop to y t. So, such type of flow is called type 3 flow. Here the outlet is unsubmerged, okay, and you have H greater than H star. H is greater than H star, outlet is unsubmerged. However, the flow inside the flow inside is only partially full. Okay. So, this is type 3 flow. What happens is your this thing also less than D. You can also have another type of flow, that is type 4 flow. We can write it type 4. I will just draw. What is the type 4 flow? Say inside the culvert, let this be the critical flow depth line. Fine. So, I can now suggest, if your this is the headwater depth h, depth of the culvert d, this is the critical flow depth inside the culvert, you may have a situation where the flow will go like this inside the culvert, and it maintains this same depth in the exit also. So, YT. So, this is the type 4 flow. What is the peculiarity here? Here also you have outlet as unsubmerged one, outlet is unsubmerged. You have the tail water depth less than d, but also the tail water depth is greater than the critical flow inside the culvert. So, that means that inside the culvert you have subcritical flow throughout. That is the peculiarity here, and you have H less than H star here. So, here H is definitely means it has to be less than H star, then only, otherwise it would have touched the boundary and all. So, that way we can classify type 4. Next one is type 5. Let me write this as type 5 here. In type 5 flows, what happens is that your depth of flow H in the headwater or upstream H is less than H star. You have a critical flow depth line, you can just draw it for the culvert. Your flow profile will be such that from here it goes like this, and at the tip it goes into the YT, that is depth YT, tail water depth is YT. So, this depth is critical depth YC. So, you have H less than H star. Now, also you have YT less than D, that is the, so hydraulically short it is YT is less than the critical depth flow inside the barrel. So, this way it can means the flow inside will be subcritical, major flow in culvert is subcritical, only at the outlet it goes into the supercritical depth YT which is less than the critical depth, right. So, in this situation the control is kept at the outlet. So, if you have a definite control here, such mechanisms can be provided, and the flow inside the culvert is also subcritical. Next, the type 6 flow you can discuss is where we can suggest type 6 such a way that, let me draw the critical flow, say if this is the critical flow depth inside this thing, and if this is the headwater depth H. So, we are suggesting H less than H star, and the flow it goes all of a sudden into the supercritical form. The flow inside the culvert barrel is supercritical, and it may just raise little bit to YT. Okay. So, what does this mean here? So, YT is less than D, that you are quite aware. YT is also less than YC. Flow inside the culvert is supercritical. So, if you want to provide supercritical flow inside the culvert, the control is kept upstream. Okay, here if you provide a control in this portion, so you will get the supercritical flow inside the barrel. So, like this we have discussed the flow types in culverts, and based on this particular course level and all, we would like to conclude the portion of culvert at this location. Next, we will discuss on flow through obstructions. What is meant by an obstruction? An obstruction in open channel flow, it is similar to a constriction. You have earlier seen what is meant by constriction. Say in a stream, if all of a sudden due to some engineering projects or engineering works and all, if the stream is getting constricted in the width, this is called constriction, right. So, you have seen that. Similarly, an obstruction is also a constriction. It is a type of constriction in width of the flow, right. So, but the difference is that in the constriction you have only one opening. So, the entire flow is getting constricted in one opening, right. In obstructions, what you face is that, say in the stream, if you incorporate a pier like this, what is it is going to happen is that the width, say here let us assume that it is B1, let us assume it is B, and here let us assume it is B2 by 2, and so you have two openings where the flow is occurring there, right. So, two openings are there when obstructions, at least two openings will be there when obstructions are incorporated in the flow. So, what are the various types of obstructions you may observe? Obstructions commonly encountered are bridge piers, or pile foundations, well foundations, piers, abutments. Many such obstructions you may see when you next time when you travel or when you pass cross a river and all, you can see such many type of man-made obstructions, or even natural obstructions can also be there that obstruct the flow. So, such obstructions also play a significant role in the type of flow that occurs in the channels. So, the flow in obstructions, it may be supercritical or subcritical. Okay. So, flow in open channels, it can be supercritical or subcritical. So, you can use the energy principles as well as mass conservation, so or continuity equation, right. So, they can be incorporated to analyze the flow in such obstructions and all. So, we can quickly suggest the energy equation, say between two sections. In the previous slide, if I go there, here if I just draw as two sections, say this is section 1 this is section 2 this is section 3 then I can just draw the cross section of this particular region. I can now easily suggest that say let this be the channel bed, then let this be the obstruction employed. So, various flow depths we can suggest now. Say let us at section 1, let us assume that it has been the normal depth there y1, then the flow it raises due to the obstruction. it reaches a certain value, it just reduces to a certain value here, then it raises like this. So, this is depth y 3 at the section 3 3 the depth. So, this is the obstruction. So, if I apply continuity equation, between section say 2 2 and 3 3. If I apply continuity equation between section, you can see that V 2 by, of course, the flow conditions are steady. So, V 2 by 2 y 2 plus V 2 by 2 y 2 is equal to V 3 y 3. So, you can now easily infer the fluid numbers. So, fluid number at the section 2 2, this is the section 2 2, and this is the section 3 3, right. So, we can suggest that V 2 by root G y 2, F R 3 is equal to V 3 by root G y 3. At both the sections, we can find the fluid numbers, we can suggest the fluid number quantities and all. So, this continuity equation can be developed like this. I can form a particular relationship now. So, from continuity equation, and in the next class we will derive or we will suggest the relationship of a particular parameter for the obstruction. So, from continuity equation I can just suggest now by squaring the terms V 2 y 2 squared is equal to V 3 cube V 3 squared y 3 squared, like this, right. So, just incorporate the fluid number and we will see, we will get a particular relationship. We will continue this portion regarding this portion in the next class. Thank you.